Now that we have a basic idea of what our ideal filter should be doing, let's take a look at some realistic but simple passive filters. And so by passive filters, we mean filters that consist only of passive components. And so that means we only have resistors, inductors, and capacitors. So once we get to our active filters, we'll be introducing some op-amps. So we're going to step through each of our filter types here. So we're going to start with our low pass, and then in later videos we're going to move on to our high pass, band pass, and band reject filters. So let's first look at our low pass filter. And we're going to consider a circuit that we had seen previously. So just this simple RC circuit. So let me just make a note. We considered this circuit previously. And the reason I say that is we're going to use some results that we had already previously derived. So the notes that are posted on Canvas, if you see page 4-2, of course this was also covered in a previous video, but from that video and those notes we had found the transfer function for this circuit, h of j omega, which in general, remember, is equal to the output over the input. We had found that to be equal to 1 divided by 1 plus j omega RC. We had also sort of simplified and found magnitude and phase. So let's go ahead and write that, because we know with those plots that we were looking at for our ideal filters, we were talking about magnitude of our transfer function. So magnitude is just going to be 1 divided by the square root of 1 plus the quantity omega RC squared. Okay, so what we can see then is we can look at this magnitude equation and we can consider sort of extreme cases. So we can say, well, what happens if our omega is equal to 0? So looking at that, we can see if we have a 0 here, that second term where the omega is will go away, and we'll be left with 1 over the square root of 1. So just 1 divided by 1, and we'll have the magnitude of our transfer function, h of j omega, is just equal to 1. Now, our other extreme case is, let's say omega equals infinity, or omega goes towards infinity. What is going to be happening then? So again, we're considering this omega here. We say if that number gets really large, it's going to dominate, and we can essentially ignore this one. And then we're going to have a really large number squared, take the square root of it, so we'll basically have omega RC in the denominator. And 1 over a really large number is going to be a really small number, and as omega gets large, that's going to be approaching 0. So we have omega j omega, or h of j omega, sorry, is equal to 0 as this omega is getting really large. So we know that this fits our behavior for our ideal high-pass filter. So let me go ahead and sort of sketch here our ideal filter behavior that we saw in the previous video, and then we're going to overlay on that what our actual filter behavior will look like. So here we had our h magnitude of h of j omega versus our frequency, and we said we had up here is 1, and we know we're going to have some key frequency omega c. And so let's do our ideal in blue again. So we said ideally it's just going to pass it, and then immediately at omega c it's going to stop passing signal. So we get something that looks like this. So again, let me just make a note. This is for our ideal case that we saw before. One other thing that I want to note before I forget to is that from this behavior here, we can say this is a low pass filter. But if we come back to our circuit, we can note that this is dependent on the fact that we defined our output voltage across our capacitor. As an interesting activity, what you could do is you could define your output voltage instead to be across the resistor, and we would see that the type of filter would change. And so the point there to keep in mind is that what type of filter you have, what type of frequency behavior, depends on where we define these inputs and outputs. So it's not necessarily an inherent property of the circuit itself, it also depends on the definitions that we apply to the circuit. Okay, so coming back to this specific case, keeping our voltage defined across our capacitor. We know we have this low pass behavior at our extremes. Now what we want to do is we want to investigate this cutoff or this roll-off frequency a little more. So let's say we want to determine our omega c. And so remember we had said this omega c is oftentimes called our cutoff frequency. It also can be called our roll-off frequency. So we want to find this value. And using the same definition we have before, this is somewhat arbitrary, but remember when we were talking about our series resonance, it was essentially a band pass filter. And we said we wanted to define those key frequencies where we say sort of we're defining our band where we had half power. So let's just keep that same definition. Again, keeping in mind that it's arbitrary. And we're going to say by definition, the signal is at half power at omega c. So 1/2 power at omega c. And I'm just going to put in parentheses, this was arbitrary. We could have also had a half voltage magnitude band. We could have had a quarter power band. But this is sort of the standard that most people will do when they're talking about corner frequencies. So what we've shown previously, and so this is on page 4-17 in the notes that are posted on Canvas, we said that this half power corresponds to 1/√2 of our voltage or current. So half power corresponds to voltage or current being 1/√2, which is approximately 0.707 of original value. So let's just highlight that. So we're talking about then voltage or current, and we're saying that's going to be 1/√2. So half power corresponds to our voltage or current being 1/√2. So coming up here, what we can say then is in our actual circuit, instead of having this sharp cutoff, we're going to have some point here that's 1/√2. And at this point, that's where our actual plot is going to be equal to the omega c. So let's see if we can't figure out what the value of this omega c actually is. So what we can say is our transfer function, the magnitude of our transfer function, h of j omega c, is equal to, so our output voltage, so remember in general this is output voltage divided by input voltage, so we're saying our output is 1/√2 times the maximum value of our input, so we have 1/√2 times VI divided by VI, which is just equal to 1/√2. So these VI terms cancel out. So now what we do is we set that equal to our general expression for our transfer function magnitude. So we had 1 divided by the square root of 1 plus omega c RC quantity squared. So we get something that looks like that. So what we can do now is we can solve for that omega c. So we can say our omega c is equal to 1/RC. Something to keep in mind though is this is for this particular circuit. So this is not a general equation for low pass filters. For this particular So this is only for this simple first order filter circuit here. So with that in mind, we can say that this omega c we know is equal to 1/RC. And so what that means is we can adjust where this frequency is by selecting our resistor and capacitor values. So now let's come back here and plot what this actually looks like. And so I'm going to do red to plot my actual curve. We said we know at our corner frequency it should be at this 1/√2. And so let me actually adjust this to make my plot look a little nicer. I've made this band a little large, so let's move this down a little bit, and so things might not be to scale exactly, but let's say we have this here, and so again, this is going to be 0.707 or 1/√2, and we're saying that up here for really low frequencies it is 1, but then it's going to start dropping off, and we should have sort of a curve function, so you can see that in the textbook drawn a little cleaner, or even in the lecture notes a little cleaner. But the basic idea is we should have a curve that looks kind of like this, as opposed to our sharp cutoff for our ideal filter. So this red curve here is our actual filter behavior. And so there are things that we can do to sort of make this closer to ideal. This is our simplest filter, our first order filter, so we can add more components to make that transition a little sharper. But what we notice is, we've seen this before as well, is that the difference here is 3 dB. So between our ideal, so at our corner frequency, the difference between our actual and the magnitude of 1 is a difference of 3 dB. And so that's why you might also see this omega C frequency called our 3 dB frequency. So there's different ways that we can describe this cutoff point. We can say it's the point where we have 1/2 power. We can say it's the point where our voltage or current is 1/√2, or we can say it's the point where our magnitude of our frequency response has dropped by 3 dB. So in subsequent videos, we're going to come back and we're going to do similar, we're going to take a similar look at our high pass, band pass, and band stop, and then we're going to look at our active filters.